Project 3.4.3, SAR ADC, the complete build. This here is the final SAR ADC build. In auto mode, you can see it go from 5 down to 0, and in manual mode, we can go back up to 5 with the press of a button. So, how does it actually do this? First of all, let's explain some of the chips. So, this here display and IC1 are octal D flip-flops. These chips here, and here are dual D flip-flops, and these are some AND gates. As well, we have the clock subcircuit that we mentioned in the previous, the second last video, and the sample and hold, which was in the last video. And then a automatic versus manual mode switch, and the button for that manual mode. So, how does it actually read the voltage here in these 7 bits from our input voltage? First step that we should mention is IC1. This is the main chip that's doing most of the work here. Its clock is tied to the clock, so it goes very fast when you're in autonomous mode. And its Q outputs are tied to the next D input. What that means is that Q1 or Q0 is tied to D1 or D0, or sorry, D1 or D2, and then Q2 to D3 and so on. This means that whatever is on that initial D line is being shifted through the chip, like a shift register. The dual flip-flops here are acting as secondary latches. They're connected, their clock pins are connected to the outputs of this IC1. And what that means is if IC1 is high, then whatever's on data here will actually latch through. And that's going to be compared with an AND gate to the, this Q output is going to be compared to this Q output on an AND gate, and that's going to the DAC. And this is what's going to determine the voltage here. So this DAC is constantly being compared with the sample and hold subcircuit as we saw before to the input voltage, and we're deriving our final voltage from that DAC. So, for example, if we had a input voltage of, let's go 3.3 there, roughly. So, you see 3.35 here. First step would be everything's cleared. So, we're assuming everything's cleared on this first step. And what that means is that IC1 is going to have nothing on its Q outputs yet before a clock cycle, and all these chips are going to be high on their Q because the preset has been set high, or set low, sorry. So these have been preset, this is cleared. Now, we get 1 clock pulse. So the D1 input of this IC1 is connected to 5 volts. When the clock goes high, that's going to be shifted on to the Q output. And only Q1 is high for this chip. Everything else is low, which means nothing's happening with these secondary D flip-flops. Q1 is going to go into the clock of this, and we know that data is high from the preset. So data is going to be shifted onto the Q. That's going to be ANDed with 5 volts, so it's going to go through, and it's going to set the most significant bit high. This is going to go to the negative input of the comparator. The positive input is the sample and hold, and that's what's going to be our input voltage. We know that's 3.35, and the most significant bit is going to represent 2.5 or 2.6 volts because this circuit is using 5.2 volts just because of the range of the input. So it's going to represent roughly 2.5 volts. 2.5 is lower than 3.3. So the comparator is going to give out a high. That high is going to go to the data inputs of the dual flip-flops. So now we have a 1 on all the data flip-flops still, on all these dual flip-flops. Then the clock cycle goes. For our second clock cycle, it's going to shift that 1 that was on Q1 to Q2. Q1 will remain high. Now on Q2, we have a high. So the second secondary dual flip-flop is going to be high on its clock, and we know it has a high on its data, so it's going to shift the data onto the Q. That Q is going to be ANDed with the high of this IC2's Q, and it's going to go to the second most significant bit. We still have the most significant bit on. So that's going to be 2.5 volts on the most significant, and 1.25 on the second most significant, which results in 3.75 volts. Our comparative voltage on the negative input is 3.75, and the sample is still 3.3. That means that our comparator is going to go low. I won't go through every process because that would take a while, but as you can see, it'll go through, depending on the comparator with the data, setting it low or high as the IC shifts through its bits to compare with the ANDs to then set that DAC voltage high or low for each bit, getting it within a 7-bit accuracy. Once again, we can see in autonomous mode, we can go from 0 all the way up to 5. Sometimes it's hard to see because even one minute movement can change the voltage a lot, so some persistence of vision effects. And then with manual mode, we can go back up to 5 volts. That's the basic premise of this SAR ADC build. So I thank you all for watching, and I hope you have a great day.